How you guys doing? I'm Lucas. I'm with the UC Rally Committee. I'm a music major, and I'm super happy to be here today. First, I just want to thank our donors. We all benefit, students, faculty, staff. We all benefit from your generosity, so we appreciate you. We love you. And I want to introduce our next speaker. So our next speaker has been with the EECS department at UC Berkeley for over a decade now and was a lecturer at Princeton from 2011 to 2014. He received his PhD in EECS in 2011 from here at Cal, and before that, he received his bachelor's in electrical engineering from UT Austin in 2003, and prior to his time in Texas, he was a dispersion of random molecules unassembled into any greater being. In 2017 and 2018, he received departmental teaching awards, and in 2023, he received the Distinguished Teaching Award. He has taught courses in AI, ML, data structures, rule-based and generative art, data science, and the social implications of computing. Please welcome Professor Josh Hugg.
Thank you. All right. Today's a marketing lesson for me. Up against us is, as someone mentioned earlier, how to find happiness. So I'm assuming everyone here is happy, and then we're going to learn some cool stuff. All right. So I'm going to tell you a little bit about computer science. And I like this old quote by Hal Abelson, who's a lecturer or a professor at MIT, where he said that computer science is not really about computers. And it's not about computers in the same sense that physics is not about particle accelerators, biology is not about microscopes and petri dishes, and geometry isn't really about using surveying instruments. The reason we think computer science is about computers is pretty much the same reason that Egyptians thought geometry was about those surveying instruments. Whenever you have some field that's just getting started and you don't really know what's happening, it's very easy to confuse the essence of what you're doing with the tools that you use. So you out there, you may think of computer science as writing programs, and that's of course an important part of it, or like the specific programming languages, but computer science is a lot deeper. Computer science to me is about taking complicated things and breaking them down into simpler things, about how to take a process that you want to enact and figure out what sub-processes you need, and there's quite a lot of depth to it. So what I want to do today is really hit you with some very specific examples so you can appreciate what computer science is. Like, what is it that we're studying? What do we mean that it has nothing really to do with computers? So I am going to use a motivating example from a programming language, and I'm going to be talking about an interesting little flaw in the Java programming language. And I picked Java for a couple reasons. It's one of the programming languages we use here at Berkeley in our second semester class. It has a lot of things I love about it. The IEEE Spectrum magazine, which is a nerd magazine about electrical engineering and computer science, has their ranking of the relative popularity of programming languages. Python is number 1 with a rank of 1 out of 1, or a score of 1 out of 1. Java is right next to it, then JavaScript, then C++, and so forth. So Java is a big deal language. And in Java, here's some code, just to give you a sense of what it looks like. Java had a funny feature in it for a very long time that I'm going to be describing today. First, just as a fact, and then I'm going to tell you exactly why this fact is the case. So for the first 25 years of Java's existence, from its inception in the 90s until the year 2020, you could make Java crash with very simple code. You read in a file, so this basically says read in this file of numbers, then you tell Java to sort it, and it crashes. And this is just a file which has specifically the numbers 0, then 40,628, then 49,544, then 11, and so forth. And that 50,000 numbers would cause sort to crash. That's kind of surprising, or like very strange to me. Like, to give you a sense of how strange it is, I imagine, for example, like you hire a plumber to unclog your bathtub, and there's like one model of bathtub that makes your plumber explode. It's just like a bizarre thing to imagine. Like, it shouldn't happen, period. That sorting crashes with some specific sequence of numbers. Sorting just doesn't feel like it should be dangerous in any way, and yet it was. And so I'm going to give you a deep look at exactly why this is, and I think it'll be worth your time. Now, this is a lecture where you have to actually think. All right, you can't zone out. You can zone out a little, but I'm going to try and draw you and give you things to think about as you go, so you walk away with something that's like serious knowledge that you can tell your kids about. Now, the reason this happens in Java is because it uses a sort called Quicksort, which is has its own very interesting history to sort numbers, and Quicksort has a vulnerability unless you take a certain mitigating measure that we'll talk about at the end. So I'll talk roughly about why this crash happens, but I think you'll really get it. Okay, it's going to take us some time. And along the way, we're going to learn a bunch of other little things, and hopefully we'll learn how to be happy. All right. So the first sort I'm going to talk about, just to give us a baseline understanding, is something called selection sort. And before I get there, I just want to talk about what the sorting problem is specifically. So sorting is the process of taking a sequence of things and putting it in order, either in ascending or descending order. So an example is you go to your spreadsheet and you say, I want to sort grades in my class. Okay. So I sort the students by grade. This is just a sample. These are real grades with fake student IDs from my class. These are the actual boundaries, which to me don't seem weird, but I guess seem weird to other people. Yeah, like a B+ is somewhere in the 70s because our exams have scores where the medians are in the 60s or so. If you go on the Berkeley Reddit, you'll see students griping about that. But anyway, if you sort the spreadsheet by grade, there has to be some process to take your sheet and sort it that way. Maybe it was sorted by name originally, and that's sorting. So let's think about this. Like, let's say you wanted to sort a hand of playing cards in increasing order. Here's some. How would you do it? In fact, we're all friends here. What do you think? Well, give me an idea. I hand you the cards. Like, what's the process? Yeah. 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 Right. So the idea was take the smaller numbers, put them on the left, and keep going until you get the bigger numbers on the right. And so I'm going to do that exact algorithm called selection sort. Hello. So what we're talking about is how we're going to get items into order. Here's some cards, and I'm going to show you a way to do that. So instead of sorting cards, I'm going to be I'm going to put numbers on a slide, and then I'm going to use the process you described to sort. Okay. So selection sorting, I'm just going to jump into a little demo. It's going to work like this. Okay, I have all my items, and the way I'm going to get them in order is I'm going to find the smallest one. What is it? Yeah, 2. Great. So we get the 2, and then we move it to the front of the array. What's an array? An array is just a sequence of numbers. Okay, so we take that 2, you stick it at the front. Okay, so I put the 2 here. I moved it to the front. And you might ask yourself, like, there's 2 different ways I could have moved the 2 to the front. This isn't super important. But when I brought this 2 to the front, there's basically 2 ways you can imagine it. One is to swap the 2 with the 32. So notice they exchanged places, but the 15 didn't move. The other way you might have intuitively thought is like, let's take the 2 like a set of cards and stick it at the front. And then basically I end up with 2, 32, 15. I'll just mention in the world of running code on computers, just swapping is faster than scooting everything over and putting a 2. This is not that important, but I wanted to highlight it. Okay, in case you were confused. All right, what I really care about is this. Let's follow, if you were a little lost there, don't worry. What I really want you to understand is this following process. The next smallest number is 15. So what do I do with this 15? What do you think? I'm waiting. Just leave it there, right? Don't touch it. Okay, what's the next smallest number? 17, and there's 3 of them, but I'm going to pick this one arbitrarily. And then I'm going to put it at the front of the items, or sorry, the back of the items that are sorted. Next smallest? 17 again. Okay, get to the front. Next? 17 again. All right, next. Now notice 19 ended up at the end because I swapped 17 and 19, because that's the easiest way to get it there. Okay, who's the smallest? 19 goes to the front, 26, 32, 41. Okay, so that's a process you can use to put items in order. All right. Now, if you just entered the room, for example, and you're like, what have I walked myself into? What I'm trying to do here is give a sense of how one can sort numbers, but you don't have to understand this algorithm for the rest of our talk today. All right. So we invented selection sort. Like we've come up with this algorithm. So what? Like, why is this useful to us? Well, one reason obviously is we could use it to sort some things. Like I write a spreadsheet program. I could actually write code, have it run. There's other things I could do if I'm a computer scientist. Like I could study its properties and I could be really excited about it. I could think about how fast it is. I can come up with variants. And if you're a mathy person, maybe that's just exciting as an intellectual challenge on its own. You can also make sort of weird art out of it. So one thing you can do is write selection sort and visualize and play sounds showing the process of selection sorting. Okay, so what I'm going to do here is a 10-second demo. Let me explain what's showing on the screen. This is an array of numbers, and the length of the bar represents the number. So for example, the number 1 is right here. The number 2 is right here in the corner. This is some big number like 98. This is maybe 99 or 100. And what we're going to do is it's going to search this whole array, and it's going to find the smallest thing and put it at the front, just like we did. And I'll tell you about the red and white in a second. Okay. Okay, so what it's doing is it's finding the smallest thing, sticking it at the front, repeating that process over and over. And then the red color is just this guy, Timo, who created this visualization. Red means the item was touched recently, and it takes a second for it to cool off, so to speak. I think the colors are a little inconsistent, but I like the feeling of it when it's running. And then green is where the smallest item just got put. It's pleasing. All right, one more time. So you're keeping the smallest item, picking it up over and over. Okay, so that's selection sort. So that's one way that you can put things in order. Okay, but there's a problem. And I mentioned this maybe fun intellectual challenge of figuring out how fast it is exactly, that selection sort is really, really slow, okay? So imagine that you wanted to take 1,000,000 items instead of 100 like we just saw, or 125 or so, and you wanted to put them in order using selection sort. Well, the way the algorithm works, it looks at all 1,000,000 numbers, and it says you are the smallest, and puts it at the front. Then it looks at all 999,999 green items, and then it puts the next one at the front. Then 9,998, and so forth. And this is just going to end up being really slow. How slow? Well, you can add up this sum, 1,000,000 plus 999,000 and so forth, all the way down to 1. There's a nice formula for this. You've all learned it at some point. But I could be lazy and just go to Wolfram Alpha. If you didn't know about this, it's a really great tool where you can just give it like kind of almost natural language. I'm lazy. And it's able to infer what it is you're actually asking, and it'll tell you, okay, the number you're looking for is about 500 billion. Okay, so that's that sum. Okay. So basically what that means is that to sort 1,000,000 items, I had to look at 500 billion things, and it's just a lot slower than it really needs to be. Okay? So often in computer science, there's like an easy, obvious way that you can code it up quickly. You have a very strong sense that it's correct, but it could be inefficient. Okay? So that's not so great. We can look at this more deeply and think about other sizes of input. So for 1,000,000 items, it was 500 billion. If we do 100 items, it's just this sum. So 1 plus 2 plus 3 up to 100 is 5,000 items. For 10, n equals 10. We have to look at around 50 items. And if we look at, I'm going to be really, to keep my numbers nice, what I'm going to do is I'm just going to say, let's suppose that it takes 2 arbitrary units of time, I don't know, you can call them nanoseconds, to look at each item. This gets me a nice round number that says it'll take about 1 billion units of time to sort 1,000,000 items, 10,000 to sort 100, and 100 arbitrary units of time to sort 10. All right, it's always good to fix your slides when you're talking. Okay. And so we end up with this pattern, which is that selection sort, if I'm sorting in items, is going to take around n squared arbitrary units of time. And that's just very slow. Right? Any questions before I continue on? Okay, just zooming out a little bit. What we did is we invented a sorting algorithm. We saw a sense of how it behaves. We didn't prove that it's correct, you can. And we showed that its runtime has this annoying feature that you have to look at a whole lot of things in order to get yourself the answer, to get your items in sorted order. Now, the reason I made it this nice round number, you might say, why did you bother doing this arbitrary units of time thing? It's because I want this really clean relationship, that it's n squared, because it'll help us when we think about our next much more clever, but still comprehensible sorting algorithm. Yeah. Sure. Mm-hmm. Right. Right.
How do you differentiate between your program being an instant answer or it's not taking time?
Mhm.
It does have to take time.
Right. So the question was, when I use a calculator, regardless of how big a number I type in, it's going to give me an answer basically instantly. What about what's different in this case? How do you take into account this fact that a computer takes more time? So one thing I'll mention with a calculator is that the operation it's doing, the way a calculator is built is it's not using some algorithm to calculate for the most part. Especially if you're doing multiplication or adding, it's got hardwired circuits where it just gets it in one go. There may be some, if you're doing a logarithm in there, it's going to run some code, but the complexity of doing a normal mathematical operation on a single number is just not going to take very long at all. Whereas when you have a million items here, it's just more work. You can think about it, if you think about the selection sort process, that animation we did, something very similar to that is happening inside of the computer. It's not visual, it doesn't make sound, but if you have a million items, it is actually really taking items and moving them to the front over and over, and that just takes time, yeah, because it can only manipulate so many of those symbols per second, yeah. Right, in some sense, the bigger the input, the less efficient it is, yeah. It's maybe a more precise way of putting it is that the time it takes to sort increases like a parabola. It moves faster than the line, yeah. Yep, that's very bad. Because we have better alternatives. Right, complexity comes in two forms. So in the class I teach, the sophomore level class, I teach them how to be efficient in two different ways. One is how to be efficient with your time as a programmer or a designer, how to break down the process in a way that you can understand what's going on. Because one thing I think is really unique about computer science is that we're not constrained by the physical world nearly as much as other engineering disciplines. People who build bridges, they have to worry about the strength of concrete, or if you're a chemical engineer, you have to worry about temperature. With computers, there are some constraints, but they're very minor in comparison. So the limits to what a student in computer science can do is what fits in their brain. And being able to take a really complicated process and break it down into constituent parts is really important for you as a programmer. That's one type of efficiency, is you being able to understand everything that has to happen when you build this design. The second type of efficiency is not wasting time on the computer. And that's a separate angle. And this is an algorithm which is simple to understand, but is slow to execute, is inefficient to run on an actual computer. Okay. Let's talk about merge sort. Now, if you've never seen this, I think this is really beautiful. And I feel like everyone, when you're born, after you do all the thing where they check your temperature and your heartbeat and your blood, your oxygen level in your blood. This is next. It's such a cool idea. You might have a hard time understanding it as an infant, but if you could, it's such a pretty idea. So I'm going to start by telling you about an operation called merge. So merging is a process you can use to combine two sorted arrays. It's very intuitive and it's very fast. So let's suppose I have two arrays. This one on the left, 2, 3, 6, 10, 11. You can see it's sorted. The other one, 4, 5, 7, 8. It's sorted. How merging works is you look at the leftmost item in both arrays, and whichever one's smaller, you put in a new array. So what's smaller, 2 or 4? 2. Yeah, see, you're my 2 guy. I love it. Next up, I've used 2, so I'm going to turn it gray, and now I have 3. That's the next item I need to consider. What's smaller, 3 or 4? 3. Next up, we consider 6 versus 4. Who's smaller? 4. So we take the 4. Okay. Who becomes yellow next? 5, right? Okay. And now we have 5 versus 6. 5 goes in. Okay. We got 2, 3, 4, 5. Okay. 6, 7, 8. Now what do you think we should do? We ran out of numbers. Just copy the rest. We know there's nothing smaller on the right side. There's nothing left. So we copy 10, we copy 11. That's merging. Okay, so given 2 arrays, you can do this process. If I gave it to you on a piece of paper, you could do it. There we go. It's fun to merge. Okay. Why is this useful to us? Well, we're going to use this to optimize selection sort. Okay. And the key reason this is going to help us is that unlike selection sort, which had that n squared shape, this is going to be n. Okay. The way to think about this is that if you're merging two arrays, you had to look at no more than two n items. That is, you had to look at 2 and 4, 3 versus 4, 5, whatever, all those comparisons. If you think about the process, it's never going to take more than 2n when you look at them. And I'm saying that without really convincing you. You can think about it later if you'd like. But the point is that it's going to be fast. For the sake of simplicity, I'm just going to get rid of the 2, and I'm going to call it n arbitrary units of time. The actual argument I use in the Berkeley class is I say, let's just count the writes. So we only have to write 1, 2, 3, 4, 5, 6, 7, 8, 9 different values. Okay, so that's how much work it takes. You'll notice I'm often just throwing away these extra constants in front of numbers. 500 billion became a trillion, 2n became n. It's because I only really care about that shape. And in the real computer science class that I do at Berkeley, there's all this math notation where we are able to formalize this notion using big omega, big theta, whatever. I don't want to talk to you about it today. So we're going to be a little hand wavy, but I hope the idea is clear, that it's going to be something that it's n-ish. Okay? And if I had anything that I feel a little uncomfortable with, like speaking today, if it feels a little fuzzy, it is, but it's n-ish. Okay? So let's think about how we could use merging to make selection sort faster. Okay. So what we could do is if we had 64 items, if we were to selection sort them, I said earlier it's n squared. 64 squared is 4,096. Okay? That's why that's 4,096. Now if instead I were to take my 64 items and I were to split them into two arrays of size 32, and then I selection sorted them, they're going to be relatively fast. They're going to be 1,024 because that's 32 squared is 1,024. Then what I'll do is take those two arrays of size 32 that are now in sorted order, and then I'll merge them, which only takes 64 units of time. So rather than taking 4,096 by doing all this looking back and forth, I break it into two 32s, do the smaller sorts, then I merge them. And the net effect is that instead of taking 4,096, which again was just 64 squared, it's going to be 2 times 1,024, which is 32 squared, plus the 64 merge. So the merge is almost free. Okay? This is good, doubling our speed. But we could do even better. Anybody want to suggest an idea that we can make it even better? Yeah? No? Yeah. Yeah, do it again. Okay, well, let's break it into 4. So we do 4 arrays of size 16. Well, 16 squared is 256. Then what I'll do is I'll take those two 16s and I'll merge them into a 32. I take these two 16s and I merge them into a 32. And now I have 2 sorted arrays of size 32, and then I merge those. So I'm going to end up with a pair of size 32 merges. Okay, that's this right here. That's 64 units of time. So these merges are really cheap. There's 2 of them. And then there's one that's 64. And then I have 4 times 256, and I end up with 1,152 is the total cost for my operation if I have 2 layers of merges, which is cool, right? So I broke it into 4 parts, and I got roughly a 4x speed up. And I think that's pretty good. Could I do even better? Yeah, I break it into more pieces. In fact, you can keep breaking it down into smaller and smaller pieces. It will not get it down to 1 unit. Like you might think, all right, this is good. I'll just break it up into a bunch of 1s. But then you still have to pay the cost of the merges. And so we'll talk about what that looks like in a sec. But what I really want to get this through to you is that by taking this big problem and breaking it into smaller problems and then breaking those into smaller problems, then yeah, while the bottom layer is a little slow, those are such small problems I don't really care. And then the merging ends up being really fast. Now, if we keep going, what's kind of fun is you don't need to selection sort at all. It degenerates into a bunch of size 1 arrays. So at the very bottom, imagine we have 5, 4, 2, 7. Okay, we merge the 5 and the 4 into 4, 5. We merge 2 and 7 into 2, 7. We merge these into 2, 4, 5, 7, and so forth. And there was no selection sorting at all. I mean, you could say we selection sorted 2. 2, there's nothing to do, so I'm done. So we end up with an algorithm that's merge all the way down. This is the thing you should learn when you're an infant, after they check your oxygen. Okay. So merging if you go all the way down and we think about the runtime, and this is getting a little technical, sorry, but I'm going to show it, and hopefully it just like it resonates in your soul, even if it doesn't go all the way to your brain. If we merge all the way down, the total runtime will not be 1. It'll be, in this case, 384. And the reason is the top merge took 64. Then there's 2 here that are 32 each, 4 here that are 16 each, and so forth. So every layer is always doing 64 units of work. Very beautiful argument. And the real argument with the math symbols is like almost the exact same thing. And now the question is just how many layers are there? So how many layers are there? So how many times if you have 64 and you cut it in half over and over, how many times till you get to 1? Anybody remember? Log base 2, right. So there's 6 layers. So the total amount of work is 384. You have sorted much more quickly. Now, if that was a little too much for you and you're thinking, I kind of got it, what I want to impart to you is just how much faster merge sort really is. So selection sort, we said with 1 million items, is 1 trillion arbitrary units of time to complete. But merge sort, because it's this in times log 2 in shape, is going to be 20 million. So it's going to be 50,000 times faster with this simplified model. If you actually run them head to head in a program, it's not going to be this dramatic because I wasn't counting everything that these 2 programs do. But this general pattern will be true that as you get bigger and bigger in, the gap in performance is just going to grow and grow and grow to the point where selection sort's basically trash and merge sort is really good. But by this simple model, if it took 1 second to complete something with merge sort, then selection sort's going to take 14 hours, which is pretty bad. And that's only going to get worse as n gets bigger, that performance gap. Of course, it's good to see this algorithm, and then I'll take some random questions or arbitrary questions. So this can be merge sort. Okay, so what's happening here is just, it's a view of the same process where it's going to be merging arrays and then combining them. Okay, so here we go. So it's merging 2 big sorted arrays into 1 big array there. That's what's happening. Okay, 1 more merge to go. So this is that top level merge, the 64, so to speak. Okay, so that's merge sort. And it's vastly, vastly faster than our old selection sort. Okay. All right. So this idea of going from n squared to n log n, it is an incredibly big deal. We found a better runtime, and it's everything. The whole universe is like made possible by this advance. And in other places in computer science where we've managed to go from n squared to n log n, it makes things possible that are otherwise basically completely impossible. So for example, the fast Fourier transform. So n squared, the basic idea is it gets really big, really fast. And just intuitively, it shouldn't take dozens of hours to sort millions of things. That just seems bad. Whereas n times log base 2 of n, that's a really slow growing function. It's a little worse than a straight line, but not by much. Can we do better? Well, it turns out that merge sort is very close to the theoretical best that you can do for sorting. We could do a whole lecture, maybe next year. Maybe I'll be up against something other than happiness, where we can prove about what is theoretically possible. But merge sort's basically right around there, close to the theoretical best. But I'll talk about a somewhat faster sort called Quicksort. That's going to be our closer. Okay, so it's faster by a bit, enough so that it's in the Java library as the way that it sorts numbers, but it has this interesting problem that we'll discuss. Okay, questions? Yeah. Who made that leap? So both of these algorithms go back so far that I don't think it's selection sort was probably invented way pre-computer. Merge sort, this is a good question. So there's a book by Donald Knuth, which is, I think, the definitive reference for the history of sorting. Merge sort, I think, also is one of those algorithms that just basically as soon as computers came out, just the people who are around realized that it's a way to do things. So I don't know that there's an inventor known for merge sort, and it dates back to, again, the very, very origins of computers. But the Knuth book would let you know. Yeah, there wasn't like a moment in time like in the 60s where it's like, oh, we've been doing it wrong. Yeah. Sorting's too old of a problem. There have been other examples like that, but this is not one of them. Yeah. All right. Quicksort. So we've seen two sorting algorithms out of the dozens of, I think, interesting distinct ones. One is selection sort, which is based on the idea of finding the smallest item. So you take the smallest item and you put it at the front. And then there's merge sort, which is based around the idea of merging. We're not going to talk about quick sorting, which uses a different operation called partitioning that is particularly weird. And it's particularly weird if you know where it came from. Okay, so this sort, which is considered to be the fastest sort for sorting numbers in most circumstances, was invented by a guy who was later knighted for his computer science skills. He invented this algorithm in 1960 when he was a novice programmer studying English-Russian translation. Wikipedia says 1959, but I think it's actually 1960. I went and listened to the interview with Tony again. He sounds pretty sure in the interview, but one of the 2 years. But the basic idea is he was working in the very beginnings of machine translation, doing the lamest possible Russian-English translation, which is I'm going to take each word and I'm going to look it up and see if there is an equivalent word in the dictionary, what is the appropriate Russian word. So here's a cat who is wearing a beautiful hat, and he has a bunch of English Russian words. His dictionary is kind of cutesy. That cat is Koshka, which I guess is more like kitty. But the idea is then after you do this lookup, you end up with some somewhat bad translation just by looking up all the words. That's the background for what Tony's doing. Okay. Now at the time, this dictionary was stored on a piece of linear tape. And so what was better to do is to take your sentence, the cat wore a beautiful hat, and then sort its words in your computer's memory, because that's small. You have enough memory to fit those words. But the dictionary was too big to fit in memory. And then you would just do one scan over the tape. So you would just go through and you'd find A, then beautiful, then cat, then hat, and so forth, and then you'd rearrange later. Now this isn't that deeply important to the story of sorting, but I think it's funny because this is why Quicksort was invented. Tony, all by himself, thinking about programming. I think he was actually in Russia at the time. He had to somehow sort his sentences, but he didn't have a sorting routine in his language because it was 1960 and there was no internet, so he had to invent sorting. And what's wild to me is this was his idea. So you came up with, let's find the smallest item at the front. That seems obvious to me. Instead, he did this, which, I mean, it's like mind-boggling. The only way to do this, it's a very strange idea, but this is how it works. All right, this is the part where I have to stretch your brains the most. So if you've drifted a little, come in. This is the part where I want you to use your energy. Let's define a partition, okay? What's a partition? We have an array, and we pick a number we'll call the pivot. It's in green, okay? When we partition, after the operation is done, there's many possible outcomes, but whatever happens, you have to have all entries to the left have to be less than or equal to the green item, and after, all the entries to the right of the green item have to be greater than or equal. So I'm going to give you guys 45 seconds to look at these 4 things and say, which ones are valid by my definition? You don't have to get it right. It's okay. So you have to think, is this a valid partition? Does it obey the rules? These all seem less than or equal to. These all seem greater than or equal to. Feeling good, feeling good. Okay, are these all less than or equal to? All of them? Yeah. How about these? All greater than or equal to? Okay. This last one, though, has a problem because 4 is not less than or equal. So those 3 are all valid partitions. That's what he's going to use as his basic idea, is that if I just had some partitions, then I can work. Now, it shouldn't be obvious to you right now, why is partitioning useful for sorting at all? But that's what he thought. Like, this is the operation I need. Not moving the smallest thing to the front. It's if I could just partition. Okay. All right. How is this useful? Well, we'll get there. First, I want to talk about how you partition an array, just so we have something specific. In this demonstration here of partitioning, the way I'm going to do it, this is the easiest way to partition. Create a new array. Then you find all the items that are less than and put them in the array. Okay, and I'm using red to represent less than. So 3, 1, 2, and 4 are all less than. Oh, and sorry, I didn't tell you something important. What's the pivot here? It's in white. It's this leftmost item. Why am I not using green? Because if you're red-green colorblind, it's hard to see. So I used white instead. All right, so anyway, so I'm going to take all the items that are less than, I'm going to put them on the left. Then what should I copy in? Yeah, all the items that are equal. And then what goes here? Greater than, great. So that's a valid partitioning. So this is an approach that will get us a partition. Okay, so that's a simple algorithm for doing it. It works. Okay. So then, how would partitioning get you to sort? Well, if I were to use that algorithm I just described, 3, 2, 1, and 4 are all going to get put to the left because they're all less. 7, 8, and 6 all get put to the right, and 5 ends up in the middle. Okay? So that's what partitioning did for me. And partitioning, you can show, takes n time. I'm not going to. All right. So how could I use this for sorting? Anybody notice anything interesting about where 5 is? It's in the 5th spot. Yeah, right. I mean, I think it's even a deeper reason, or deeper observation. It's where it needs to go, right? So 5 is in its place. It's where it'd be if the array were sorted. So in some sense, you can think of partitioning as it does two things. One, it sorts that pivot and gets 5 in place. So it sorts only the 5. And then the other thing that does that's really important is the two halves are now separate. So the left half are only those items which are smaller, and these are only those items who are bigger. So if you want to just crudely, you can think of it exactly sorted the 5, and it kind of sorted the smaller items, and it kind of sorted the larger items. That's partitioning. Now, how Tony decided that's the way to sort, I have absolutely no idea. And even more crazy to me is that he decided to name the sort Quicksort, and then it just happened to be the fastest sort. This is like very strange that he got lucky with that. Now, our convention, when we do this, oh yeah, go ahead. Yeah. Right. So my convention, great question, is I'm always going to use the leftmost item as the pivot. But you could have chosen some other thing. So I'm always going to say whatever item was in the array at the leftmost side, that's going to be the pivot. And then we'll use that process of coloring them red, white, and blue to get them in this order. So if the question was, how do you know 5 is the pivot? Because I decided the leftmost item should be the pivot. Does it make sense? And then how do you get it in this spot? Well, you do that, copy all the smallers, copy the equals, copy the biggers. Okay. So then when you continue this process, you end up with 2 subproblems, one that's 3, 2, 1, 4, one that's 7, 8, 6. And then where will this 3 end up if we partition this? So what will be here when I push the button? 1 and 2. And because I'm doing the lazy version, I'm just copying them in their existing order, it'll be 2, 1, 3, 4, and so forth. Okay. And then we have the separate problem over here. Okay. Let me do a little demo of this one. All right. So when we quicksort, it looks something like this. We pick the leftmost item, then we partition, and we end up with 15, 2, 17, 19, 26, 17, 17, 41. So that's that process, okay? So that was the partitioning just of the 32. And then we do the left half. If you trust the recursion, it just works. And then we quicksort the right half. I have a longer definition. Like if you want, we could do the whole thing here, but I don't know that it would be that satisfying. But I have it linked in the slides. So if you're up late at night tonight and you're like, I want to see that whole demo, you can go to yelkey.com/now and look at it later. But what I want you to really get is just a rough sense of what partitioning is. Okay. All right, let's do one more of these guys. So this is what Quicksort looks like when it runs. Okay, so when Quicksort runs with a bunch of numbers, the partitioning process, what just happened is these are all the items that were smaller than the pivot. These are all the items that are larger than the pivot. Now there's one little annoyance is that Tony Hoare's original partitioning strategy actually used 2 pointers that come towards each other and like things get swapped around instead of our strategy of coloring red, white, blue, and copying. It's not worth your time. But if you watch this and it doesn't seem exactly like what you remember me saying, it's because it's slightly different. Still partitioning though. These are all the items bigger, all the items smaller. a little more chaotic than merge sort. Give a hand a Quicksort. Okay, anyway. Okay. All right. So let me tell you a little bit about Quicksort's speed. So as I mentioned, Quicksort was just the name that Tony picked, like very cocky move to name it Quicksort, and it just happened to be the fastest. And so what I'm going to do is I'm going to run some code, and we're going to run merge sort versus Quicksort real quick. So I'm giving it 10 million numbers. I'll see how it goes on my laptop. Okay, here we go. So on my laptop, Quicksort took 712 milliseconds, and merge sort took 1,253. So good job, Quicksort. And the fact that Quicksort's faster isn't really something that you can prove. It's more of an empirical fact. Now, Quicksort has a very strange property, which is that it can get unlucky. Like if I run this over and over, it's always going to be roughly this same speed. But if I give it an input that it doesn't like, it can be very slow. Okay? And so what I'm going to do is think about what can happen with Quicksort. This is the last thing I really have to stretch your brain with a little bit. So in the best case, the best thing that can happen for Quicksort is that the pivot always lands in the middle. And then these new pivots that we always land in the middle. And then these new pivots, the pivot always lands in the middle. So we have a pattern roughly like this. We're always cutting the universe exactly in half. That's going to be our best case. As we saw with the merge sort idea, cutting things in half over and over gives us great performance. Okay? So there's only size 1 problems. We're done. This is the best thing that could happen. Okay? So what's the runtime? Like, do you think this is going to be n squared e or n log n like merge sort or something else? What's your gut feeling? You don't have to prove it to me. It's okay. It's faster than merge sort. That's a great argument. We just did the experiment. It's merge sorting, okay? So you could do a proof that looks like this. You could say at the top level it does n work because it has to partition and takes n. Then we have 2 n over 2s. Then we have 4 n over 4s. And the overall runtime is the same as merge sort. So it's almost the same argument. There's a little bit of a difference. I'm not going to point it out to you. I don't want to confuse you. But it takes roughly n log n time. That's the best thing that can happen. Okay. Let's think about the worst case. The worst thing that could happen is that the pivot never moves. So first question is, what numbers could you put in these boxes to get this pattern? And the second one is, if you did that, would that be like merge sort, like selection sort, something else? So what would cause the pivot to stay here? If it's the small, yeah, if it's 0, okay, then what could this be? I don't think max, something else. Yeah. If it's max, the pivot would end up over here. Yeah. So if the smallest value is in the leftmost position, it doesn't move. What would this one be? Second smallest, right? So if we gave numbers like 1, 2, 3, 4, 5, 6. If you told Quicksort, go sort a sorted array, what it will do is it will partition, and it'll take n time to do nothing, and it'll put the 1 here. 2 won't move, 3 won't move, and so forth. So the overall runtime is going to be just like selection sort. It's going to look at all 5 items, then all 4 items, 3, 2, 1, and so forth, taking n squared. So in some sense, the fact that we studied selection sort was very useful to us. It let us understand, I mean, maybe, at least intuitively, that in the worst case, where the pivot never moves, you basically end up with the same situation as selection sort. So basically, if we think about it, in the very best case, it's like merge sort, but faster. And in the worst case, it's n squared like selection sort. Now, it might seem strange, right? Remember, n log n to n squared was a super big deal. Like I said, it's civilization changing. Maybe not in those words. So how could it be that Quicksort's faster? Well, it's that on average, it's n log n. You have to be extraordinarily unlucky to get that n squared behavior. It basically never happens. If you want, there's a whole PhD thesis that a guy I worked with at Princeton wrote studying this. I have not proven it to you, not even remotely. But if you run a bunch of experiments, you'll see it's usually n log n. Okay. So empirically, we saw earlier, quicksorting is usually faster. But theoretically, we saw that it had this danger, this n squared situation. And I don't know why Quicksort's faster. I've never, in many years, never found anyone give a convincing explanation. As far as I know, it's just you run some simulations. So the last thing is, do we really need to worry about that worst case? And if so, how do we deal with it? And that's what we're going to close out. Okay. So let's try and make Quicksort safe. All right. Actually, first I'm going to tell you where the danger. The danger is bigger than you might have realized, which is that if I give it 1, 2, 3, 4, 5, 6, it's going to be pretty slow. They might say, well, that's only one possible permutation. But even if it's almost sorted, it's still going to be pretty slow. So it's not enough to just say, like, let's check and see if it's sorted. If it already is, don't do anything. Like that, I always have students suggest that. Because if you have an array that's almost sorted, you can show that it's basically almost as bad. Okay. So here's a question for you. Maybe my last serious, well, actually, I got a couple more. So in an ideal world, let's imagine we wanted to pick a pivot here. What pivot should we pick? So this is the numbers 1 through 9. Who's your best pivot? Yeah. 5, right. Why? It's the halfway point. It's the median. So really what we want is one solution we could do to make Quicksort safe is the first step when you pick a pivot is instead of using the leftmost, which is dangerous, we always use the median. So you could always use the median, but the problem is the computational cost to find the median makes Quicksort slower than merge sort, so you're stuck. So it's a beautiful idea. Like if instead of always using the pivot I'm left with, I use the actual median, then you end up with an algorithm that's no longer valuable because merge sort's faster, okay? What's something else we could try? I don't know, anybody want to throw out another idea? So picking pivot or picking median as pivot, too slow, merge sort wins. Other ideas, yeah. Sample and pick a median, right. So approximate the median. Great. This is what Java did until 2020. Other ideas just for fun? I'll give you one that's actually the most popular, which is randomly pick a pivot or shuffle the input before starting. This works, but programmers don't like randomness when it's not necessary because then your code is hard to debug, unpredictable. Okay, we're going to fix our punctuation and spelling though, because this is Berkeley. Okay. All right, so those are some approaches. Then there's another one, which is if we're taking too long, give up and switch to merge sort or something safe. This is what Java does now. Okay, actually, Java still does this with the backup plan below. Okay, so these are all strategies that we talk about in my class. It gives you a sense of the kind of depth you can come up with to design your way out of trouble. Okay. Now the trouble with your approach, which was let's just approximate the median, there's a guy named Doug McIlroy who is 92, still a practicing mathematician. I actually emailed him 2 days ago when I was getting ready for this talk, and he wrote me back, which was cool, because I think of him as a legend, you know. Any Taylor Swift fans here? No, because they're all grown-ups. But imagine emailing Taylor Swift and getting an email back in an hour. It's cool. You know, that's the nice thing about being a computer scientist, because all the famous people, they're not as famous, so they'll write you back. Anyway, the trouble is that there's an algorithm you can use to generate an array that if you're using an approximation of the median that is fast, you can always find a poisonous input that will break Quicksort. What happens then? The reason that this array breaks Quicksort, that causes Java to crash, is that the pivot's always landing in the same place. This is the sequence where the pivot gets stuck. And the way that recursion works in Java is that if the recursion depth of a program gets too deep, it will crash. Okay, all right. Now in 2020, Java 14 got released, and silently they added a change, which is that if the recursion depth, and I didn't tell you what that means, but it's basically like how many sub-problems deep you've gone, right? So how many levels? If the levels go beyond 64, then it switches to heap sort, which has good performance no matter what. It's not as fast as Quicksort. And so I don't know. I emailed the guy who added this. I haven't heard back to know why did you wait so long, but that's why Java crashed, because the pivot got stuck in place. So now when your kids ask you, why did Quicksort crash? You have an answer. The pivot didn't move. Go ahead. Yeah. Yeah. Yeah.
Well, I thought something like 0 or 46.
So this specific sequence of numbers, I haven't shown you the algorithm that gives you this sequence, but with the specific pivot strategy that Java selected, like basically any strategy used for picking pivots is going to have some poisonous input. If you use leftmost, it's the sorted order. If you use some particular like sample and use the median of those, this is the sequence where the pivot always gets stuck. There's a lot of details I've hidden, but if you run Quicksort on this sequence, that's the sequence where the pivots you're picking get stuck every time. The difference between Java's Quicksort and the one I do is they don't use the leftmost item as their pivot.
Is this something that somebody wrote in their brain figured out, or they use a computer?
So this sequence of numbers, so the algorithm to devise this was come up with someone's brain, but you run on a computer to generate that sequence of numbers. Yeah, and that's its own talk. Yeah. Yeah, let's do it. It's time. It's time. Well, thanks everybody. So yeah, we covered quite a lot of ground. We're at the very end. So if you'd like, I have all these other sorting algorithms that you're happy to, or you're welcome to run and play around with. And yeah, this link will work for the next 24 hours. So thank you everybody. And now you know about pivots. See ya.